Am I audible? And is the screen visible?
Yes.
Okay. So last week's assignment was okay after the tutorial? You could solve the problems?
Yes.
Good. So now that we know about the theoretical idea of hybrid automata, now we'll switch on to LHA, linear hybrid automata, timed automata, and how do we use them to verify the designed cyber-physical systems. Okay, I guess have you gone through the new assignment, week 7 assignment? How, I mean, were you able to solve it?
No, I am not able to understand. Even your first question is itself, I am not able to understand.
Okay, yeah. After this, I think discussion, you will understand, I guess. So yeah, let's start. So theoretical ideas, did you understand? I think there are some gaps in understanding theoretical ideas. If you understand theoretical ideas, these things will be understood as well. We will first go through the slides as we go, and we'll solve some problems on this chapter. I made some problems. We'll solve them together. So yes. So do you know feedback about other students? I don't see anyone else joining.
Actually, I am a working professional. I am not a
Yes.
student. So
I
I
know.
don't know about students, but I am finding this course very difficult.
Okay. So were you there in professor's live session?
Yes, I was there, but only 15 minutes. After that, there was no one.
I mean, I think they waited and they left since nobody joined. Did you join from the start?
I started, and then after 15 minutes, I saw nobody was there.
No, no. Did you ask any questions and that was unanswered or something? Hello.
I attended that 15 minutes, but after that, everyone left. There was no one.
No, no, no. You have. I mean, that is for doubt clearing. If you have doubts, you can ask, and it will be answered.
No, I thought okay, after some time I will ask till I understand it, and all are left.
You should have asked.
Okay,
Yeah,
okay.
that is the purpose of the I mean, that session. Anyways, so fine, you can ask me. Please join the next session as well and ask questions. Whatever you have doubts on, you can ask them. I mean, I'm asking because I can see very less number of people are doing good in this assignment solving. Some are doing good, but very few. Anyways, so yeah, so linear hybrid automaton we have studied. So hybrid automaton had these things in its tuples. I hope you remember them. Now if we think about LHA, LHA has a slight different tuple. So LHA is, as you can see from the name, so it specializes in modeling the linear systems, LTI systems, linear time invariant systems. So whenever we need to analyze their reachability or analyze their safety, all these things, so we use linear hybrid automaton instead of the generic class of hybrid automaton. So this is a specific type of hybrid automaton, you can say. So obviously there are locations, and there are transitions between those locations, and there are invariants. Invariants are basically convex linear predicate on variables. What does this mean? So linear predicate that are convex, that means the region that you will be mapping via the invariant, basically how does the invariants look like? So invariants are like so invariants will be like if x is a variable that you have in HA, so invariants will be invariants on x will look like something like this maybe. If x is of obviously if small x is in real and only one dimension, then this is how an invariant looks like. It can be any real number. So basically if you plot this in a plane, if you plot this, basically how will you get it? So if this is a plane for you, and if you try to plot it, if that is for only one variable, if you are trying to plot it, so how does it look like? How does this look like, this invariant? So if this is 0.5, this particular,
You are writing something, it is not visible.
oh sorry, okay, hold on. Visible now?
Yes.
So yes, so basically when we are saying that this is 0.5, right? So how does it look like? Basically this looks like this whole area, right? It can go here as well. That is how it looks like, isn't it? So this area that I am mapping here, so basically this is what, this is sorry, I'll make it transparent or something. So this area that I am coloring here, so this goes beyond this. So there can be some if it is of 2 dimension, maybe say it is of 2 dimension, so x and y, there are 2. So now your invariance looks like this, y greater than 0.2. So what does that mean? Again, if, you need to know where is the 0.2, and based on that you can understand where your whole I mean the firstly this is x and y axis. I'll just write them down. Sorry. So this is, I'll name them x1 and x2 to help you understand that x is made with those. So x equals to basically x1 and x2. Obviously it will be transposed, this will be transposed. So that is how we write it like, we write it like a column vector, right? So yeah, so if this is 0.2, maybe I am telling 0.3 like this. So basically this is how it should look like, right? So if this is x1 and this is x2, this is x2, and if this is the region that you are trying to find, and this is basically 0.2, and here you will have minus 0.3. Is this understandable what I'm trying to say?
Yes.
So whenever x is in this position, basically I am telling that that is an invariant condition for a certain location, certain location. So maybe when the x is here, we be in one location. Maybe when x is beyond this, we be in another location, maybe. Okay. So yeah, we be in some other location. So this is how it looks like. So it changes the location accordingly. So if you see it goes to infinity again maybe. So at least it looks like it always will look like a half plane. If not a fully enclosed area, it will always look like a half plane. Okay. So usually the boundaries that you are getting, that will be convex. Convex meaning any point that you choose that will that is within the x and y terminal values of this maybe in this x2 dimension I am starting from minus 0.3 and 0.2. Now within these points, if I choose any of the points that has the value maybe say 0.1, so any points that is having an x2 value with 0.1, that will be inside this region. So this is an example of convexity. So this is just trying to simplify the system that we are considering, nothing else, for linear hybrid automaton, so that whatever system that we deal with has a location, as an invariant location like this. So what I am trying to say here is basically we are changing locations based on the value of the state, valuation of the states. And yes, here we are not using x as the valuation like we did, I think we did that, yeah. Here I think we used x as the valuation of the continuous state variables, but here I think we are having x as the set of state variables. Okay, in this case our set of state variables is x1 x2. So yeah, now we can have multiple locations depending on different invariant conditions, and obviously as I explained, those are linear. Why linear? Because the formula that I wrote, if you remember, this is a linear equation, right? Or it can have a linear combination of x1 and x2. It can be something like this. It can be anything like it can follow any equation. So this will have another block or another shape that is totally closed, or it may be half closed. It can be unbounded in one side, but obviously there is a safe region that is fully bounded. So if we intersect, we'll come to that. If you intersect the whole region with this invariant region, then we'll get a closed region. So we'll come to that. So what I am trying to say here is the invariants that we consider for location L, that is basically I am writing invariant x because I am considering invariant as a function. So I should not write like that, I should change it. So if I consider when the invariant is here, that is basically and location L1, basically this is the invariant for location L1, and there is an invariant for location L2, maybe this is the L2 location invariant. So whenever the state is here, it is in one node, one location of the hybrid automaton. Whenever the states are here, it is one location of another location of the hybrid automaton. So yes, so flow relation in each location may be different. So in this case it is a constant. That is why the overall hybrid automaton progresses following a linear equation. Okay. So valuation function v, basically this is mapping the values of state variables to real variables. So for a transition t, guard gt. So basically again, since invariant is a property of location, we write it as invariant in bracket the location. Since guard is a property of the transition, we write it like guard on a transition. And again, this is also a linear convex predicate and the variables. Reset t again on the transition t, it is again using the basically resetting, the assigning certain values to the state variables, denotes shall be so it is basically relevant to the transition that I am using. So this is the definition, basic definition. Now semantics, predicate p, we are defining it, the things that I was saying. So it has to be true in order to stay in a location. Yes, this is important. If you see, the system state starts at L with V, then after tau is the time. So by default in a linear hybrid automaton, if you notice, we are considering a clock variable that is increasing with respect to time. We had the same for hybrid automaton as well. If we consider explicit clock variables, how does it become? For that we will try to understand what is timed automaton, and by merging the concepts of timed automaton and the linear hybrid automaton or hybrid automaton, we express any system in form of an automaton, and then we can verify the system and its reachability and safety. Anyways, So we'll come to those things. So yes, so here if you notice, after tau time, basically since I started with this valuation, this is the valuation function, right? V is a valuation function that takes the variables as input and gives you current valuation of the these states. So, and this is the flow equation in location L, okay, for these states, okay. So since it is linear, so it will change, it will be a constant value. Since it's a linear hybrid automaton, it will be a constant value. So if you multiply that with time, so basically this is same as integrating a constant value for a tau amount of time from 0 to tau, isn't it? So your initial value is basically this, and you're integrating this constant value for 0 to tau. Is that understandable what I am saying?
Yes.
So this is what you get after tau duration. So and now that you have a new evaluation, based on that, how basically this is how the whole thing is changing, and this is how we write the not discrete, time elapsed transition. Basically here if you see, we are not changing the location, we are changing the valuation. How we are changing the valuation? We just expressed how we change the valuation. If tau time is elapsed, this is how the valuation changes, and we denote that with V prime. And yes, so transition, this is a transition from L to L prime, and it is in this set. We have a discrete step of label between these two states. Yes, so we are labeling this transition with this state. Now this can be any predicate, like this is basically a guard condition. So you see here, basically you are considering G is the function that we use to denote the guard condition, and that is using this label. So this label is a guard condition, basically that is this label notifies that a guard condition that is denoted for that particular valuation at that moment is true. I think we should write true here, because you may confuse with this transition set. Anyways, so this means true basically. So what it is trying to say is, when guard is true, and with this label following this valuation, you are moving on to L, from L to L prime, and V prime is your new valuation of the variables, where you are resetting, maybe you are applying some resets on the variables on the change on the label. This is a label that you are using to transit from this location to this location, and reset out of that label, we are denoting that with reset A. Like we are finding out the guards out of the A label as guard A. This is just a way to express them. You can define and express it however you want. So this is not specific, so we are just expressing it this way. So yes, you are resetting some of the variables, you can reset some of the variables, it's up to you how you design it. So you can consider this as a transition, valid transition of the in the hybrid automaton. Basically V0 satisfies initial condition, INIT L0. So INIT is what we had in tuple. So that is basically the initial valuation of the variables. So reachability problem is basically given an LHA A and a set R of linear regions. Linear regions, again, what I just showed, that is basically linear regions. Okay, this is how we express linear regions. Quadratic, if it had it been quadratic, it would have been a circle, or it could be a parabolic region or something like that. Anyways, so ellipsoidal region or something like that. Anyway, so linear regions, we are basically simplifying the domain that we want to study. We can study for the whole possible systems, but we are here studying for only for the linear time invariant systems, and only giving the reachable regions as linear regions. So basically, given an LHA A and a set R of linear regions, if there exists a reachable state of A that belongs to R. Okay, so that is what we mean by reachability analysis. So basically I am trying to find out if there exists a valid valuation that intersects with this linear region, that wholly intersects with in linear region, that does not go out of this linear region, or if it reaches the linear region, depends on my specification. So basically I am trying to find out if there is a valuation that falls into this linear region or not. So that is the idea of reachability analysis. So continuous successor, yes, and this is interesting. So P is a linear predicate. As I was defining linear predicates, this can be an invariant basically defined on x i's, and L evolves like this. As I said, x dots are now constants here, flow equations are now constant, so we are considering this as a constant value. And predicates are basically next predicate is denoted as maybe p prime. So you are basically trying to find out that since you know the equations for xi is basically flow equations for xi is basically ki. So this is where you were before tau amount of time, right? You are starting now. So before tau amount of time, this is where you started from, right? And this is the new predicate. Basically, you are trying to find out if there exists a tau that is greater than equals to 0, and for which you are defining a predicate, and that predicate you are defining as p prime. So continuous successor is this. This is what we define as a continuous successor, because as the time is elapsing, how the continuous variables are changing, the predicate is depending on that. So discrete successor. Discrete successors are basically jumps between two locations. It can be jumps to the same location again. So if you notice, this is on the edges. So basically this is while we are in a location. Continuous successors are how predicates are being evolved when we are in a certain location, because in every location I am following a flow equation, which is a continuous time equation for continuous time variables. And during discrete jumps from one location to another, or to the same location, maybe we are resetting certain variables and we are checking some guard conditions, right? So these are discrete transitions, and discrete successors are denoted like this. So basically new p prime is basically the resets that we have in this edge from L to L prime. Since reset is a edge property, basically this is how we write resets, and some resets are basically, you can express any reset as maybe I am resetting x to and value a, so we can write the reset as x minus a equals to 0. So that is how we are denoting the resets. So based on these resets, the predicates change. So this is basically discrete successor. So this is understood?
Yes.
Okay. If these things are understandable, then we go to post operation. What is post operation? Post operation is basically helping me evolve along the time. Okay, as I evolve along the time, I go through multiple continuous and multiple discrete successors, right? So, and that is how my linear hybrid automaton or hybrid automaton evolves towards a new location or to new valuations or new states, and eventually I will be finding out if that is reachable to the new valuations that I get, if that is intersecting with the desired region, linear regions that I desire to reach in that amount of time. So that is what we call reachability analysis. So basically P1 is nothing but your input is a set of linear regions, obviously in this post operation, output a set B of linear regions, initially empty. So you are trying to find out what is the set B after one post operation meaning one continuous successor and one discrete successor. After one continuous and discrete succession, where do you reach? So for all L comma P, location and the predicate belongs to A. A is the basically set of linear regions that we have taken as an input. So we are starting from this region. Okay, all possible predicates that are defined on this region using the state variables, obviously. For all L comma L prime, basically this is the edge that I am considering as the discrete jump. I have to do the following. So what are the following things? Basically P1 is basically the current predicate value that you have while you are in the location L. You are ending the guard condition in this edge with this predicate, and you are denoting it as P1. consider it like steps of a program that you are writing in order to find for this input regions what should be your output region, while you have a defined hybrid automaton. How do you find that out? You start from a initially empty linear region, and you AND the guard condition that you have on each of these edges for all L comma L prime. L prime can be any edge in the hybrid automaton. So you find out, you mark that as P1. Now using P1, how do you compute P2? Basically this is a discrete successor of the P1 that you just computed, that is basically intersection of guard conditions and the existing predicate in the location. So here you are basically finding out what is the discrete successor, and along with the discrete successor that you are denoting with P2, now you are entering the new location L prime, right? Discrete jump is done, you are entering the new location L prime. There you are basically ending it with new invariant. So if you have a new predicate, that is P3, now P3 will be used for continuous succession and you get P4. How do we use it for continuous succession? This is how we use it for continuous succession. So basically we know how the variable is changing, so we use that. So we are starting from certain x and we are reaching to some x value. We know how it is evolving. So yes, so after that again, while we are in that location, we have to abide by its invariants after continuous succession. After every continuous succession, we have to always keep on checking that if we are abiding by the invariants of that location. So for that you are denoting with P5. Now what you are trying to find out is existing B that was initially empty, obviously, what is the L prime comma P5. P5 is something that you have computed till now starting from the initial condition, initial predicate. So this is the newly computed predicate after continuous and discrete successions. So what is the region that you reach to? This is after one post operation, this is where you reach. This is understandable?
Yes.
Okay. So we'll use this while you are analyzing reachability, and we'll use this multiple times, and this is how we denote it. We are basically trying to make things easier, so we are denoting it with a post, and I is the initial region, so we are taking that as input, because post will change based on the initial region, because I am considering this for only one hybrid automaton or only one LHA. So that properties of LHA are not changing. What is changing is my initial region that I am starting with. So for all possible k in natural numbers, you are basically finding out all reachable states. This is what we denote as post star, like we use in regular language. We use A star, B star, right? So basically post star means I am progressing for multiple continuous and discrete successions, and that k value, how many times I am having discrete successions, can span through the natural number range. So this is how I compute, and obviously after this I have to find out it the region, the linear region that I am desiring to reach is never empty. Intersection of this post with the desired region is never empty, then only my design is right. So I am reaching where I desire to reach, that is, and abiding by all the rules that I have framed in my LHA. So this is how it looks like. I think this is clear. So here are some examples how reachability analysis and verification is working. I think there are some examples as well, and we ran it on some systems using some tool called HYLA. HYLA is for hybrid system reachability analysis. So this is how it is run. These codes are, again, this is the exact code that it is that is written in these tools. This is how it is done for each post operation. Okay. So yeah, this is another system. So fine. Now to understand the notion of time, how the time variable is evolving, we come to the idea, we try to understand the idea of timed automaton, because while we will be verifying this system, no, we'll be verifying the safety of these systems. The time will be a crucial variable that we need. So to understand the concept of time, how do we integrate the concept of time with the continuous variables, we come to the timed automaton definition. Basically they have a new set of variables called clocks. So these set of variables are like the state variables we have, but they take real values and they increase. Basically their flow equation is basically 1 always. So as the time progresses, these variables also progress. Okay, now I can reset them as I want, obviously, but they only progress. Their flow equation always defined as the progression of the clock, same as the progression of the real time clock in your machine. So that is how we simulate a system using these clocks. So again, the definitions are pretty much same. So I'll go to the definition. Yes, the only thing you will see different is there is a accepting state like we had in regular automaton and finite automaton while we design finite automaton. So we have an accepting state to find out what are the valid sequence of transition. We call them valid timed word. So timed word is something that we get out of the timed automata trace while the timed automata is running. So if it is reaching an acceptable location, basically we call it a valid timed word. So I will not go through each of these definitions again. Yes, one important thing to notice is basically edges are from locations to locations again, and they can have different possible set of clocks in the reset. So if you see, this is basically 2 to the power x means power set of this set of clocks. So we can reset any set of clocks in these edges. Okay, so this is why it is written like that. And yes, if you notice, all the guard conditions will be looking like this. So x, some operation c, such that x belongs to x, the set of clocks, and c belongs to some natural number, and the operation will be among these. So either less than equals to. So these operations will be used. Basically we are binding the clock variables with certain value. So this is how the guard condition will look like here on the clocks. So I hope this is understandable. This whole idea is understandable what you are trying to do here. Hello.
Can we take some example to
Yes. We'll go through some examples. Yes. So before going to example, I'll just show there is a new kind of transition here. If you see, last we saw continuous transition is there and discrete succession is there. Transition, succession, however you call it, it might not be a transition. That is why we are not calling it a transition while we are in the same location. Basically, it's not a transition; it's a succession. Okay. So basically, if we are changing the locations, we call it a transition. It depends. It's just wording, how we define things. That is up to that. So here in this case, we call these transitions when we are, see here we are staying in the same location, but with tau amount of time, the valuations of the clock variables are increasing like this. Do you notice the similarity with the linear hybrid automaton? Here we had with the initial values of x, we increased it based on whatever equation we had for the variable. See, this is how you used to change values, update the valuations, right, when we are in a location. So those are for state variables. Here we have clock variables, right, and this is how the clock variables are changing. So if you notice, the f, the flow equation is always 1. There it was constant. Here, since these are clock variables, so they will change as the time changes. This is understandable. So we call them delay transition basically. Okay. You understand like why we are calling it delay transition, because we are not changing the location, we are just updating the clock value. And in discrete transition, what happens is we are basically changing the locations based on a discrete jump, This label again can contain certain guards and certain resets, like we always we always said. So this is the maybe new valuation of x that we are going to. This valuation is on x, so we are denoting it like this. So basically it's 0 if x is in y, y may be a set of values. We are checking if the clocks are within a certain values, then it's 0, otherwise this is how it's evolving. So basically this is a this is how the timed automata transition occurs. So we are starting from L0 V0. After t1 amount of time we go to L0 V0 plus tau 1, and after discrete transition where you are having certain guard and reset conditions, and based on that you are changing the location with maybe this updated valuation. So this is where you reach, and after you reach here you again have some delay transitions, and with that delay transition basically you are going to the new maybe you are staying in the same location with a new guard and reset condition, you are going to a new location. So this is how it proceeds. So let's see one example as you are asking. So this is visible.
Yes.
So this is an example timed automaton. Okay. So always remember when the timed automaton is starting, we are basically starting, we have two clock variables here if you notice. So all the guards, the invariants, whatever we are writing. So we'll write the invariants by the side of the locations, we'll write the guards by the side of the transitions, guards and resets both. So if you see the only variables that we are using here are x and y, so you can easily guess that the clocks that we are having here are only two, those are x and y, right? So what it is asking, check whether the following timed automaton will ever reach the state C at 5 seconds of starting from state A. So it is saying it will ever reach a state C at 5 seconds of starting from state A. So before solving this, let's solve something. Let's find out a valid timed word in this automaton. Okay. So always remember the clock variables will start with 0 value, because that is when I am starting we can call it simulation, or we can call it the execution of the time trace, finding out the time trace, how a system works. So basically the system is started, then the clock variables are always initialized with 0. Okay. So this is how we start. A is the location, x is the valuation of the x variable, x equals to 0, y equals to 0 is the valuation of the y variable when we are starting. Where do we go moving on from here? So see here, there are no invariant conditions here, right? So we don't have to bother about that, but let's consider the accepting condition is C. It is not mentioned here, but from the question I am trying to basically they are trying to understand it if it will ever reach a state C at 5 seconds starting from state A. So let's consider C as the accepting region. Okay. So considering that, if we start to find a valid timed word, what will we get at B? When can we enter B? From this guard condition, what can you say about that?
X is greater than 2.
Less than equals to 2. So
If
guard,
X is,
yes, can please tell.
X, if X is greater than 2, then only it will go to B condition.
No, basically guard condition has to be true in order to have the transition. So if there is a guard condition in the transition, that is I was saying, right, that is what I was explaining, right? So this guard condition is what it has to abide by in order to have this transition, discrete transition from this location to this location. That is how we define the guards, always, for hybrid automaton, for timed automaton, anything.
So that means if X is less than 2, then only it will go to B.
Not less than or equals to 2.
Okay.
So then only it can move on to B. If it is not, it is going beyond 2, basically what should happen? It is trapped in A, it cannot go out of A, so it is not reaching the desired location. So you can consider this as an invalid timed word. If I had something like this, maybe I reach somewhere like from here, starting from here, I am reaching somewhere like you are reaching somewhere like A, comma, x equals to 3, comma, y equals to, what should be y equals to? What is the value of y? What are x and y? X and y are clock variables, right?
Yes.
Clock variables. So clocks, how do they change along with time? When I say x equals to 3, what do I mean? Time is passed, 3 unit of time is passed, elapsed. This is a delay transition, right? That we just saw in the example, right? Delay transition here, right? After 3 units of time, valuation changes like this. So here after 3 units of time, valuation changes like this. So y should have what value? Same. Yes, yes. So since both are clock variables, as I was saying, clock variables will always change in the same amount as the time changes. So these are basically measuring times, and we are having different variables to measure different times in different locations, maybe for different events, maybe. That's up to us how we design it. How we use those variables is up to us. So yes, so this is a valid word? No. So this is not a valid word if we consider L as the accepting invalid word if C is in L ACC, right? If C is the accepted location, then this is an invalid word. Is that understandable what I'm saying?
Yes.
So if I move on to B, with what value of x can I move on to B?
X is less than 2.
Right. So let's write it here. Why is it not coming? Hold on. Hold on, it's not responding. Fine. Yes. So B. What can be a possible value for B? Again. Should have kept it somewhere else. Anyways, I'll just move it here. Just keep it here. So x equals to, let us consider something like this works like, right? What do you think? This works?
Yes, yes.
So yes, this works if you consider that your clock can have non-integer values, like it can have, it will obviously be positive value, but it can have float values as well. Then less than 2 equals to, if you want to simplify things, we can consider that your clock only works for the integer values. It's up to you how you design things. If this, it is like if you consider it in seconds, basically it is 1.5 seconds. If you consider it in milliseconds, then you don't need the float value, you can consider it using integer values. So I hope you understand. So what should be the value of y? If I am having jump at tau equals to, let me write it here. here, then it will be clearer. So at tau equals to 1.5, I am jumping, discrete jump. So what should be the value of y?
Less than 2?
Why?
Less than or equal to 2?
Why did you say that? Why do you think so? Explain.
In fact, if it is less than 2, then only it will jump.
No, I gave that condition on x, not on y. Noticed?
But in B, if you B C,
Yes.
from B to C, it is less than 2, na?
I am entering B now. You need to worry about this transition, not this one now. So here, while I am doing, understand this very well. When I am having a discrete transition, what should I take care of? When I am in a location, what should I take care of? I should take care of the invariants, right? That is clear. When I am having a transition, what should I take care of? I should check whether my guard condition is true and whether I am resetting based on the policy that I am using. These are the two things that you have to remember. That is how you update your predicates, right? We showed it. That is how you update your predicates while you are getting the continuous and discrete successors, right? So here also in timed automata also you are not updating you are updating transitions in the same way. If you remember, delay transitions and the discrete transitions, right? So what will be the value of y here? So what do you need to take care of in this transition? Guard condition is taken care of. This is less than 2. That is why I am allowed to transit to B, and y should be 0, isn't it? Why 0? Because I am resetting y. Don't you see? Do you see? Is this understandable what I am trying to say?
Yes, yes.
If I would have reset y minus 3, then I am resetting basically y to 3. Is it understandable what I am saying?
Yes.
Anyways, so now we have y value with 0. Now we can have the next. What should I check here now while I am in B? What did I just say? What should you take care of when you are at a location? The invariant, right? Invariant condition. What is the invariant condition here again?
Y less than 2.
Y less than 2. So see this. So while you are in A, you can only come to B when x is less than equals to 2. So within 2 units of time, right? And then you are saying you can only be in B for 2 units of time because you have reset y and started counting how long you are staying in B, staying at B, right? Understanding what I am trying to say?
Yes.
And while I am at B, then only at any time I can go to C, because the guard condition says what? Y less than equals to 2, right? Is that understandable?
Yes, yes.
So is this a valid timed word? Tell me. At initializing with this, so I am changing, having the discrete transition at. So if this is my next state, when am I having the discrete transition? Can you tell me? Hello. Are you facing difficulty to answer this? What is the problem that you are facing while understanding this? I am asking, at what time am I having the discrete transition? If this is the valuation that I am entering B with.
Y less than 2.
Why did you say y less than 2?
Because once we the time is less than 2, y in B, then only it will be in B.
No. I am repeating again. There is no guard condition on y here.
I'm talking once it went on B, once that is on the B state.
No, I am asking you if this is where you are starting from. Okay, listen to the question very well. This is where you are initializing from. Okay, and this is the next location that you are going to with these valuations. Then at which time are you transiting to B? If this is the valuation when you just made the discrete transition to B. Did you understand the question?
X less than 2 or equal to 2?
Yes, that is my guard condition. I am telling what is at which time am I transiting to B so that I get this valuation of the clock variables. When do I get x equals to 1? At
time is equal to 1.
Then obviously I am jumping from A location to B location after one unit of time, right?
Yes.
That is why this is a valid word, I mean I am progressing correctly towards a valid transition, right? So after this, if x has 2.5 valuation at the same location, what should happen? Am I allowed to go to C?
No.
Why?
Because in that B location, the time limit is only for the 2 seconds.
Where did you get that in from this description?
In fact, at B there is no X ka value, it is only the Y value.
So what do I mean by that?
B will go to C only when there is a condition on Y.
No, I am telling to stay in B, what is the invariant? While I am at location, while I am having the transitions in the same location, I will take care of my invariants. While I will be changing the locations, I will take care of my guards and resets. This is clear. Now tell me, I am being in the same location. Tell me, with this value of x, first question, can I go to C? Second question, what should be the value of y? Is this a correct value of y?
X doesn't matter because there is no condition on X at B.
Correct.
Y,
correct. Yes, carry on, please carry on.
Y, only Y matters at B. So Y is, if it is less than 1.2, less than 2, it will go to C then.
No. I am not asking about going to C. Understand this very well. First question is, what should be, is this valuation correct?
Yes, it is correct.
Why?
Because in that, okay, X doesn't has any meaning. Y is less than 2, which is satisfying that.
Okay, so this is also correct?
Yes, this is also correct.
No, this is not correct, sadly. Why is this not correct? How do they evolve? You are only taking care of the discrete jumps. You are not thinking about the delay transitions or the continuous transitions in the locations. So see this very well. So when I have the value of x as 1, I have the value of y as 0. I am at B. And how are they progressing? After 1.5 amount of time, what will be the value of x? Starting from this?
2.5.
And after 1.5 amount of time, what will be the value of y?
It is also 2.5.
Y is also 2.5? Why?
Yes.
Why? I mean, it's okay. Please explain. Why do you think y should also be 2.5?
No, because I think both will increase in the step
No,
of
you
one.
are intuitively thinking that you know the specification, but the specification is written here. You have to strictly follow the specification here. Here, while you are entering B, do you notice that we are resetting y?
Yes, yes.
So this is what we are starting with. With these valuations, after 1.5 amount of time, what should be the valuation of x? Again, I am asking. 2.5, you just said. What should be the valuation of y? Now you tell.
Because it is resetting, so it will 1.5.
So this is wrong. Do you understand why? While x is having this value, y cannot have this value while I am at the same location.
Yes, yes, yes. Understood now.
So understand the specification from the automata very well. Then only you will follow what is happening and what is not. Fine. Now that this is also valid, from here can I move on to C? That is the next question that I asked. So from here, can I go to C? What do you think?
Yes, because transition, in that transition y is less than 2, so here y is 1.5, so we can move to C.
Right? Correct. So y is less than equals to 2, so we can obviously move to C because there are no guard conditions on x, so I don't bother about x and I move on to C. So this is clear how it is working, how a timed word
Yes,
is
yes.
valid. I hope all the possibilities that you could make things wrong, you have tried and you have surpassed that. So we have corrected that. So now the question becomes, can it reach C after 5 seconds of time, at 5 seconds of time? Tell me. At 5 seconds of starting from state A, can it reach to C? What do you think? So what is the new word that I am trying to find if it's valid or not in this case? So I'll copy this, I'll duplicate this, let's try to solve it. So I'm starting from here. I'm trying to find out, will I be here at I don't know when I am changing the location at B. So tell me, when can I make the discrete jump here? So will it ever reach this valuation? Is this a valid word? Can a valid word end with this? This is the question, right? You understand that, right? What I'm saying?
Yes.
So let's go back to what we just solved. Here we can see C is having x is having 2.5 here, right? So starting from state A, will it ever reach state C at 5 seconds starting from state A? So at x equals to 5, where will I be?
So in B state also we can take x is equal to 5 instead of 2.5.
In B?
Yes.
Yes, we can take, we can stay longer in B. That is what you are saying? That is what you are saying?
Yes, yes. In B state we can stay 5
We can
instead of
stay.
2.5 we can stay here at 5
Why?
seconds.
Can you really stay at 5 when you are having a transition at x equals to 1? Because what will be the value of y then? If this is 5, then what is the value of y?
We cannot have, because y can, then y is equal to 2
Yes,
in that case.
yes. So the answer will be no here, right? It cannot reach at C. If it has already reached C, then it can stay up to 5. Do you understand what I am saying?
Yes, yes.
But it will never reach C at 5. And why? For the reason you just told. It cannot, because construction of so you understand this, the timed automata idea is, I guess you have understood it very well.
Yes, yes, now understood.
Okay, moving on. So these things we have seen, we have learned what is accepted timed word, there are examples. This is very important. Invariants ensure progress. So do not, if there are no invariants, your clock variables will not allow you to stay. There are no conditions on how long can you stay and when should you go out. Do you understand that? So at a certain location only you can stay if x is less than or equals to 5. If there are no invariants, you can stay as long as you want. So this is actually helping you progress, right? Helping you move on to different location. So that is why invariants are very important. And if you notice, you are mostly missing the invariants while you are evaluating the values, right? So be very careful about that, because these are very important. So yes, there is a very nice example. You please follow this example that professor I just taught very well in the lecture. So there are other examples as well. I am skipping those. Those are very well explained in the lecture, so I am not going through them again. So let's come to the main thing that we are trying to do after learning all these things. So propositional logic formula is not new to you, I guess. So you have studied this. So it looks like something like this, using and or. Considering these are basically Boolean variables, and if you are considering the first order logic formula, basically those are also something like that. But here you are considering the real variables, and you are basically considering the relations between them, and you are trying to find out if they are true or false. Basically those cannot be, might not be Boolean variables, and this is how you are expressing the first order logic formula. So this is something I guess you understand very well. So now representation of Boolean formula, there are different way to represent this Boolean formulae. Why I am suddenly talking about Boolean formulae, I will come to that. Why it is needed to find out the reachability or the safety of a system, I will come to that. How it is analyzed and how it is verified, to do that we need to understand this. So basically a Boolean formula can be transformed into conjunctive normal form CNF or disjunctive normal form DNF. So what is conjunctive normal form? Basically you are ANDing two different properties or two different variables. So you are ANDing the you are basically ORing them, and such clauses are ANDed together. Okay, CNF has form of many clauses ANDed or conjuncted together. Okay, is that understandable?
Yes.
DNF is the dual of it. It's exact dual. Basically multiple clauses are basically ORed or disjuncted. So basically CNFs are mostly preferred. Why? Basically, why? Because they are solvable in polynomial time. Polynomial time conversion to CNF from any Boolean formula is possible. So what we are trying to find out is, if we have a first order logic like this, first if we convert it to CNF, then basically it is easier to do this satisfiability solution, find out the satisfiability solution. Standard way of finding, a standard way of giving input to all SAT solvers to find satisfiable solution is this CNF formula, because that helps us in terms of complexity. And in polynomial time we can convert any formula in terms of CNF formula, so it will cost me only a polynomial amount of time while you are converting any formula into CNF, while you are trying to verify that formula. So satisfiable, what do I mean by satisfiable? Have you I mean, I think you all must have, you might have you might not remember it now, but yeah, satisfiability formulas are basically something where you are trying to find assignable set of values to variables to make the given formula a tautology or make it true. Okay, so you can see here for certain values of x1, x2 and x3, basically you are finding out that this whole thing can be true. So these are basically its satisfiable solutions. Is this understandable what I'm saying, this basic idea of satisfiability formula? Okay, so these are basically two set formula when each of the clauses are having only two of the Boolean variables. So this is the simplest form of the set equation. There are k set formula, that means that there are k such things, k such literals, that we say literals, k such literals in each clause. So yeah, it is that basics of SMT. Yes, from SAT there comes SMT. What is SMT? SMT, the very basis of SMT is basically SAT formula, but SMT has basically, the name tells what it is doing actually. Satisfiability modulo theory. When we say modulo, is basically we use modulo operator to find out the remainder. So using theory on satisfiability formulas, whatever we get is basically SMT. So this is basically expressing, instead of using the first order logic, we are using the instead of using the predicate logics, we are using the first order logics here. So this is how a SMT formula may look like. So phi is an SMT formula. You can see x and y, using x and y, this is a first order logic formula, and here basically they can take any real values or I can restrict their valuations, and now they much more resemble with the continuous variables that we have in our LHA definition, isn't it? So we are basically trying to find out for which valuations we can satisfy this formula or something like that. So we are converting that problem into a satisfiability or SMT problem. And obviously, since we are using the theory of linear algebra or something to solve this particular formula, for which particular values I can reach here, and if any of those values are having an intersection with the non-zero values of z, that is what I'm trying to find out, right? So while trying to do that, basically we are using SMT, satisfiability module theory. So some theory along with the SAT solving, that is basically SMT. So there are different SMT solvers. I think these are very well explained in the lecture, so I will not go through them. So yes, what is important is bounded model checking. So now this is a hybrid automaton, right? It can be a timed automaton as well, but here we are considering a hybrid automaton, and this is basically expressing a what? This is what? This is, I think, light switch. Okay. So light switch had some specifications. Based on the specifications, the designer designed this automaton. This is a state diagram. Basically, whenever a system is designed in any platform, any hybrid system is designed in platforms like MATLAB, or there are other platforms, there people first draw a state flow diagram. This is basically a state flow diagram. So this state flow diagram is nothing but the hybrid automaton that we are going to draw. So that can have the clock variables, that can have the continuous time variables. So using them, they are writing different logics, and they are writing how they are evolving inside each of the locations and how they are changing between the locations, and they are trying to find out if the system will be working as desired. To do that, they either do reachability analysis, and to find out if the system behavior will remain safe, they do safety verification. So bounded model checking is basically checking the model by simulation or by simulating all possible states. You are trying to find out within a bounded amount of time where is it reaching or is it abiding by a certain safety property. Okay. So here it is not same as simulation. Simulation we do for a certain initial condition, but here we are trying to find out for a set of initial conditions. So if we start for a set of initial condition, if we start simulating, it will take a lot of time, right? So instead of doing that, we use SMT formula to find the reachability, to do the safety verification or the reachability analysis, however you call it. Or there are different methodologies, set based methodologies, which helps you understand, like we learned in the reachability verification part of this lecture. There were tools. What were they doing? Basically, you are giving them what is my initial position, what is my initial condition, like we learned here, what is my initial condition, and after multiple post operations. Basically, when we say bounded model checking, basically we are bounding the number of post operations. Okay. So after these many post operations or after these many discrete transitions, if you are intersecting with this region, so there are set based methodologies that help you analyze this, that can be also used, or you can use SMT based methodologies that we are going to learn in this part of the lecture. So what I just said made sense, why we are learning this, why this is important while designing system or before we implement the system. Hello.
Yes.
Okay. So bounded model checking. So yes, while we are progressing through the hybrid automaton, like timed automaton, it is same as timed automaton. We have seen how do we progress through a timed automaton. Now we'll, with the same knowledge, we'll progress through the hybrid automaton, and eventually we will encode them as first order logic formulas, and we will encode them as CNF formulas, so that we can give it as an input to the SAT solvers. Is that understandable what I just said? That is what we are going to learn.
Yes.
Fine. So how does it progress? I will skip this. I will actually go to the template. That will, is there anything important here? I think this is very well, I think these are the things that I just said. So we will see this via an example. You go through the lecture to understand this in detail, but I will take you through an example and try to elaborate this. But before that, I need to show you the template, how do we progress. So yes, this is the template. So you have an LHA or HA like this. We have learned this. This is the hybrid system model for M. So a satisfiable equation solution, you are trying to find out psi n. What is psi n? Psi n is nothing but bounded evolution of this hybrid automaton, bounded succession of this hybrid automaton, or n number of post operations, initializing from a certain valuation of these variables. After n number of successions, if I am satisfying the formula, negation of the formula phi. So if I get a true value for this, that means basically there exists a valuation for all these copies of these variables at each of the discrete succession. So if you notice, these are basically the valuations of the same variable, same set of continuous variables at different number of successions. So after 0 number of post operation, this is basically initializing. Initial valuation is this. After that, after n successions, you are reaching this valuation, and you are expressing the n successions as a first order logic formula using psi n, and basically you are finding out if you are conjuncting that with the negation of the property that you intend to satisfy. If you are getting true, that means the property, there exists a valuation, a set of valuation for the variables for which you might end up not abiding by the desired property. Do you understand what I just said? Hello?
Yes.
So basically, if you find such a valuation of the continuous time variables, basically you are telling that there is a problem, or there must be some correction in the modeling, or there must be some correction in the initial valuation, something, because it is sometimes it might have some valuations for which it may not abide by the property that I want it to abide by. Okay. So how do we formulate psi? That is what we learn here. So basically we start from the INIT condition. INIT condition is already given as part of the specification of hybrid automaton. So initialize this, then while we are in this particular location, what do we take care of? Invariant and flow equation, like timed automaton, same as timed automaton. For timed automaton, inside a location there are delay transitions, here we have continuous successions. So this is how they are changing, and for every iteration, for every succession, the valuations after every successions must abide by the invariant at that location, and after that, if it is abiding by certain guard condition to jump to a new location, it will jump to a new location with certain resets, guards and resets. And here we may have some other resets. So here basically we are writing this separately because we are trying to match it whatever we learned before we started learning hybrid automaton. Before we started learning hybrid automaton, our systems had a closed loop. We learned how to design a closed loop system, right? So consider the x variable is for the system and the u variable is the input variable, and this is a program that you have written to update the u variable based on the valuation of the state variables. That is how we write the controller program, right? That is how we update the control input, right? Using certain gain that we compute, right? We have learned this. How can you do it delay aware way? How can you do it by pole placement and all these things? So that is how we update this particular variable, and then based on the valuation of the new valuation of this variable, we again run we again have a continuous succession, and again we change the location and something like that. It goes on, and after n such post operations, if we are anyway satisfying this particular formula, that is what we are trying to find out. Is this understandable? Is this template understandable? This is a common template while we are trying to verify the system. So now let's come to an example. Let's see. Now I am taking you back to the maybe fourth lecture or fifth lecture where you did not learn the automata yet. There, how did you learn the system as? Like the system used to evolve like this. Can you tell me here? I am considering x1 and x2 as state variables, and u1 and u2 as control input vectors. So basically, x dot is like this, and u is equation of u is like this, and there are some conditions. We will not come to that now. Now with this, can you tell me what is a and b? How do you derive a and b from this, if this is given?
Hello.
Hello, was I audible?
Yes, yes, yes.
So I am asking, if this is how the x dot is expressed, can you find out a and b from this?
Yes, yes.
You can. So I am not going to that, because it is very easy. You have to consider this a column vector as the states, and basically you will find 2, 1, 1 minus 0.5. So basically it will look like this.
2, 1, 1 minus 0.5.
I think so.
Exactly.
Yes, yes, yes. I think so. I'll just the size of it. So my new A matrix is what? Tell. 2, 1
1,
and
1
1 comma
minus 0.5.
minus 0.5. If this is something that I have, is the system stable or not? How do I find that out? I find out the eigenvalues, or I can find out the poles after making the system. So this is a continuous time model, because I have written x dot, not difference equations. I have written ODEs, right? So here you can see it is unstable, right? Why unstable with these eigenvalues?
Lambda should be less than 1. Modulus of lambda.
No, no. For continuous time system, it should be less than 0, right? In the left half plane, continuous time system. This continuous time system, right? X dot equals to
Yes,
something, this
yes.
ODE, right? So since it is more than in the right half plane, so it is not stable. Along with this, what is B? If you notice, B should be something like, I have two inputs, right? So B should be what? B should be, I guess, what should be B? Tell me.
2 minus 1.
2 column vector, or
Minus
what should it be like?
minus 1.
Minus 1. So it is a row vector, is it?
Yes, yes.
It will be a row vector.
No, it is a column vector, I think.
If it's a column vector, then how will we then we will have to multiply it with u1 and u2. So basically we will have to write it like this, because u has 2 dimension, right? So we can multiply u with this one. Then can we multiply u with this one? Hello, can you multiply u with this one? What do you think?
B is column vector.
If b is column vector, then what is the dimension of u, and can you multiply u with b?
No, no.
Then what should we be like? What is b here? This is not
B is,
correct
B
thing.
is row vector only.
Okay, if b is row vector, then what is the output that you are expecting? B into u should be of the same dimension as x, right? Will it be like that? If b is row vector, then it is basically 1 cross 2, and your u dimension is 2 cross 1, right? You will
Yes.
end up having something 1 cross 1, but you have two states. You cannot add a into x, which is of dimension 2 cross 1, with something of 1 cross 1 dimension, that is bu, according to your definition. So b is not a row vector or a column vector. What should b be like? Tell me the correct b from the equation here. It's easy. Isn't it? Now if you notice, you can multiply u1 and u2 as a column vector with it, and you will get something of 2 cross 1 dimension, right? This gets multiplied with u1 and is used in the equation of x1. Notice this. This is multiplied with u2 and is used in the equation of x2. Is this understandable?
Yes.
This was easy, so I guess you understand it now. Okay, clear?
Yes, yes.
If this is clear, then tell me what is k from this equation. What is k? How does k look like? K into x should be u, right? U has a dimension of 2 cross 1, x has a dimension of 2 cross 1, so k should be hello, am I audible?
Yes, yes.
So this is very straightforward. This we learnt in the last lectures. Can you try to solve this? What should be my k? Sorry, can you see it now? What should be my k here? Try solving. So basically k will be having something, k into x, you will get u1 and u2, right? So u1 equals to something into something into x1 plus something into x2, right? So here u1 equals to what? 0.5 into x1, right?
Yes, yes.
And minus 0.75 into x2, right? What else? u2 is this is k. This is b into k. Sorry. So this is your new eigenvalues.
So what we have calculated, we calculated a minus bk, then we have calculated eigenvalue of that.
Yes, not a minus bk, it should be a plus bk. I have never said it should be a minus bk. It is depending on the case. I mean, what is the value of k? You should find out if it is stable or not. If it is minus k, then only I am not writing here how u is behaving. I have written here clearly. It is not minus k. It is minus k if I am adding a minus to if I am considering this as minus. Do you understand what I am trying to say? U equals to something into x, that something is k. Now that k can be negative, that k can be positive. Here we are finding out that particular k, and we are trying to find out a plus bk and trying to find the eigenvalue of it and trying to find out if that is stable or not. It is clearly not stable, right?
Yes, yes.
Why is it not stable? Why is it not stable?
Because the roots are complex.
No. For continuous system, it is very normal to have complex root. Why is it not stable? For the same logic, I told the system is not stable.
Yes, because that it is right hand side. Roots are at right hand side.
Correct. So I have taken an example here. So it is probably not correctly taken. You can design the control laws as you want. I am trying to express you that whatever you learned till now, how to bridge that with the currently what you have learned. So you can easily compute how the system will evolve. Right? This is how the system is evolving under this controller. Right? But now let's get back to this. So here if you see, I am giving a description of the overall system where I am telling this is followed. What I just said is followed. I think I deleted something. So I am saying this is followed only if x is in this region. Can you see this? Is it understandable what I am saying?
Yes.
And if x is in some other position, maybe I am defining that locations here, some other regions, then this is how the system should evolve. Now you tell me, how do you design a hybrid automaton for this system if you are trying to find out starting from the normal mode. Normal mode I am considering, I think it got changed, hold on. So this is what my normal mode looks like when I am within this region, and this is my critical operating mode looks like when I am in this region, and this is how the system is changing. So with this, can we find out whether the system will ever reach somewhere beyond this? Because this is my safety criteria. I am telling my system states should always be within this region, should not violate staying this property. So if I am starting from the normal operations meaning my x variables, the state variables are having a valuation within these values. Starting from that, within 2 seconds of starting with normal operations, if the control inputs are actuated every 0.8 seconds, then am I safe? That means, is my x value always within this? This is what I am trying to find out. Is it clear what I am saying? Hello?
Sir, please can you repeat it again?
Yes. So you understood the system definition, how the system is evolving based on different locations, regions, sorry, different valuations of state variables, how it is evolving differently. Now, what I am intending to do is, I am telling that is the system safe? Find out if the system will be safe. What do I mean by safe? I mean safe when the system states are within this region. Will the system states be within this region when I am starting from normal operations and after 2 seconds am I staying safe starting from normal operations after 2 seconds from starting with normal operations? So this is what I have to find out. And another property is the control inputs are actuated every 0.08 seconds. So what do I understand from all these given the criterias? That the property that I want to verify is this. First thing, right? Is it clear what I am saying?
Yes.
Second thing, initial condition. How does it looks like? I am starting from normal operations. That means when am I in normal operations operating mode? When the x value is this, right? So this is my initial valuation of x. Is that clear?
Yes.
These are all given. I am just jotting them down. What is my periodicity of control actuation?
0.08 second.
In bounded model checking, or post succession count, or discrete transition count, you can call it anything. What is a discrete transition count for which I have to check? It is given. Tell me. How many times do I have to unroll and verify if x is within this property is hold or not? How many times do I have to unroll the system? Considering that I am considering a discrete system where I am actuating once every 0.08 seconds. So how many times do I have to unroll? How many discrete transitions after I have to check this? So I know I have to simulate and not simulate. Let's not use the word simulate. After 2 seconds, I am asked to find out if the system is safe or not, right? Starting from normal operations. So 2 divided by my sampling period, I will get how many unrolling I should do, right? Hello.
Yes, yes.
So this should be around how much? 21 maybe, I don't know. Not 21, 22, I guess, something like that, right? So now we know all these things. So basically we have to find out this is what you have to find out, right?
Yes, yes.
Right? This is what you have to find out.
Yes.
So see how you are decoding the actual system specification and converting it into a specification for safety verification or reachability analysis. Now let us see how the hybrid automata will look like. So how the hybrid automata will look like? The hybrid automata will look like this. Sorry, I use a negation here. I remove this here. So I am considering two locations here. One Q norm, another one Q crit. Why? Based on different valuations of x, I have different flow equations, and accordingly I have different locations for each of them. So what are my variables here? X and u all are my variables here, right? Is that understandable what I am trying to do here? Is it clear?
Yes, yes.
Okay. So here I have, again, I am considering this as normal f, this as critical f. So I have two different flow equations here. Initial valuation I have already given, and that normal operation is the initialization condition here. So what else is left? Invariant. What are the invariants here? Invariants are, there are two invariants. While I am at normal location, then basically this is my invariant, right? When I am at critical location, this is my invariant, right?
Yes.
And if I am going outside this invariant, basically that is what I am considering as my guard condition. Okay, I'll write it as norm to crit and crit to norm. Okay, there will be two guard conditions. Whenever I will be going beyond this, I will go to the critical condition. Whenever I am going again coming back to this, maybe I am going to the normal mode, and I am following the new flow equation and everything. Okay, so yes, and what are my reset conditions? So my reset conditions are, again, I'll this is the wrong way to write resets. I'll correct them. So basically, what am I resetting every time I am having a discrete transition? Can you tell me? What am I resetting here? What am I resetting here? Every time I am changing positions, basically what am I resetting? After every 0.08 second, I am updating, I am resetting the value of u, isn't it? This is a discrete transition, this is not continuous. So updation of the control inputs can be considered as a reset at certain valuation of the clock variable. When the clock variable that is counting my sampling period is reaching 0.08 seconds, then basically I am resetting the value of u with this, following this formula. Is that understandable?
Yes.
Since I don't write the clock variables here in the description of LHA, so I am not writing the clock variables here, but if you have a different set of clock variables, you can write them here. Basically what you need to do here is you need to express two different clock variables, to one to find the global time, so that you can measure the 2 seconds time, overall 2 seconds time you have to measure, that is for global time GT and local time maybe, or H, you can call it anything. Okay, so had I been writing the clocks in the definition of the LHA, I would have written something like this. So basically I can use clock variables to model such a system, and this is how the hybrid automata will look like. Is this understandable what I just explained?
Yes.
So now that we have seen that whenever we are progressing, we are basically doing what? I'll go back to that slide and I'll try to explain. So I'll come to this example. Where is the, yes, here. So how am I, no, here, sorry. So yes, so how am I doing it? So if I want to write that psi n, psi 22 in my case, how do I write it? So let's try to write it. Let's try to write psi n. Let's duplicate it. Now we know the definition of LHA. I am removing it. Now if we want to write psi 22, let's first write psi 1. That is one post operation, right? One discrete transition, however you tell it. So we will start from normal mode, INIT. What is my INIT? This, right? Sorry. After this, where am I going? If you follow the how they are building this psi valuation, so we are starting with the initial values. Okay. After that, what are we doing? We are trying to find the continuous successions, right? Continuous successions are what? When we are at a certain location. So since I am in this location, I will follow which equation? This equation, isn't it? But what I am forgetting is I am not telling what should be the values of u. Along with this, I also should initialize u. Done. I know the values of x, whatever x1 and x2 values are there. Along with that, this will be there. This is how I am starting. And then I am having a continuous succession. What does that continuous succession looks like? It will look like, basically it will follow this. Since this is a linear formula, it will exactly follow this, and it will multiply it with the amount of time that you are having the succession for, right? Sorry, 0, right? This is how you update x. Okay. So hold on, this is how you update x. So if you multiply it with this, yes, I'll just break it down into multiple formulas. It is easier this way. Yes, so x, let's not use that notation, let's use something like this. At iteration 1, after one post operation, x looks like this. Here I am denoting different copies of x as x0, x1, that is at those timestamps or after those many discrete successions. what is the value of x. So this is understandable what I just did. I should write it
Yes.
formally. So while we are in the location, which location are we in now? Which location are we in now?
Normal.
Yes. So what should we check while we are in a location? What should we definitely check? Invariant, right?
Yes.
So what does this mean? We have included the initial condition here. We have included the continuous succession here. Now what we are saying is we have to check the invariant of that particular location. And how do we do that? This is how we do it. So basically, for any time while we are having the continuous succession, right, the time is bounded within 0 to 0.08. That means within one sampling period while I am evolving, I should always be within the I should always follow the invariant predicate, the invariant condition. Is this clear?
Yes.
So actually I don't need to write equals to true. Basically whenever I am ANDing something, basically, and that is a Boolean thing, basically this will be a linear formula, and the formula is basically this in this case. So I will write this is true, this should be true, right? Now what else is left? What else is left? Now that continuous succession is done, checking the invariant is done. What should we do next? If we want to jump to a new location or not in the next discrete jump, what should we do? So our reset formulas from normal to normal or normal to critical, there will be multiple edges, and in those edges there will be reset formulas, right? So those reset formulas will reset which one, which value of which among the variables, basically that will update my control variable, right? So after this invariant check, I will have to check if there is any transition possible. So I again update my u variable with these values. After 0.08 seconds. So this is the reset. I will write which is here instead of for. Before doing this reset, actually I should check the guard also, because I am talking about transitions, right? So what is my guard condition here? Guard condition is again same. If I want to be in the same location, after every sampling period I am checking whether I am in this position or not, in this region or not. That is my guard condition. So how will my guard condition be look like? First I will check guard, then I will reset. I cannot reset before I checking the, because guard will only tell me if I can make the transition or not. So sorry. So this is how my guard condition looks like. While I am having a transition self loop, this is basically self loop from normal location to normal location again at every 0.08 seconds. So basically I am trying to find out if I am still in the same position on if I am abiding by the guard condition or not. So this will be 1. Okay, and I will reset these values. So yes, this is one post operation. Is this understandable?
Yes.
This may look very big, but this is basically pretty basic. Nothing much. That's just the notations are very difficult to understand, but they are not difficult if you understand how they are defined. Okay, so this is for one post operation. So after 22 of such operations, you will have a big equation that will be followed by this, and that is what is shown here, I guess. Here. Now if you see, here we have used integration. For LHA, integration and multiplication means the same, because integration only lead me to this, right? Instead of this multiplication, see, instead of this multiplication and addition, if I would have integrated, that also would have given me the same thing, right? Because this is linear hybrid automaton. Do you understand what I am trying to say? Basically what I am trying to say is, this is same as writing this. This is starting from 0 to tau. Now this tau can be 0.08 in this case. So integration, it is difficult to write in integration, so I am writing here. So basically, or I can write in a better way, taking this. So this is basically starting from 0 to h and getting this out of here and putting it here. I don't need this. Or if I have a tau here and this is what you are getting. So if I do it maybe something like so these two things are same. Do you understand that for linear hybrid automaton?
Yes, yes.
So that is why it is expressed like this. So nothing to be confused about. So first you are trying to find out if there exists such valuations at every discrete transitions after every post operations. This is for all locations. You are checking this, that initializing, then ANDing, continuous succession, then basically checking the invariants. This is checking the invariants for all the time that you are staying in that location within the sampling period, whether you are abiding by the invariant condition. Okay, so along with that you are having this invariant condition is it is abiding by the invariant condition or not. Okay, that is what it is checking, and it is given by an implies. Basically, if this is the value that it evaluates to, that implies, and if I am in that location, basically invariant is satisfying this valuation. So along with that, from 1 to n, this is for initialization. After that, for n many steps, you are giving 1 to n, and you are checking guard condition first for transitioning from q to q prime. Okay, these are the valuations of variables. Then you are updating them following the continuous succession, and you are checking the invariant in that particular location. And obviously, if there is a reset will also come here. Okay, so after this, if you are having any satisfiable solution with this, is that understandable? Is this understandable? This whole thing, how this is coming? If
Yes.
you get a system like this, you can encode them now. Sorry. If you are given a system like this, like I described, I have not even drawn the hybrid automaton, and without drawing also I think you are able to understand. If a hybrid automaton is drawn, then it is even easier to understand. If you follow the template, first initialization, then you have to do the continuous progression, then you have to check the guard condition or the reset condition if you are willing to transition. Then after that, again to a new location, again you check the continuous progression, and along with that you check the invariant condition. Like this you can carry on, and finally you have to cross check it with the desired negation of the desired property. So I am guessing now you can solve it if you are given a system or a hybrid automaton.
Yes.
Fine. So now I suggest you to try the assignment that is given. I think it will be easier now. And see, finally it is nothing but finding out the a minus bk. Basically here the a that you are deriving is not correct, because you have to discretize that a and b with respect to this, because you have a self loop after every 0.08 seconds that is checking whether you are in that particular state or not, and it is updating you accordingly, isn't it? Do you understand what I just said?
Yes.
So yes, accordingly you have to update and check and update. So yes, what did I do? Anyways, so I guess now you should try to solve the questions that is given in the assignment. I think you will be able to solve it. It is very simple. If you are given to ask to solve it for 22 iterations, basically you have to discretize a and b, you have to find out a minus bk, you have to unroll it for 22 iterations, and then whatever x value that you are getting starting from an initial value, you have to find out if that value is lying in the desired region or not. It is that easy. You just have to do some computations using MATLAB or using any computation software that you want to use. Is it clear now?
Yes.
So I suggest you to solve the questions that are given in the assignment. I will upload this tutorial if you want to again go through this so that you understand what have I done. Fine. So I'm ending today's session here. Any questions that you have? I think that covers the whole thing here. So any questions that you have? Today's tutorial was helpful for you. Any questions regarding that? If not, then I'll end it here. Hello.
Thank you, sir. Thank you.
Okay, fine. Bye then.